Hi, I'm Zixuan Chen from the Data Lab at Northeastern University in Boston. This is joint work with Professor Peter Manolios and my advisor, Professor Mirek Redwood. From our title, you can see that we pay homage to the original Why Not paper, but adding the word yet shows our context of top K rankings. Let me first introduce a little story so that you can know what a why not yet question is. I'm an NBA fan. I know Curry was doing great and won the championship last year. To determine whether Curry was good enough for the MVP award, I came up with a simple linear function like this, adding up points, rebounds, and assists with equal weights. However, Curry is not among the top 5 players. Now I'm wondering, why has Curry not shown up yet? This is the why not yet question in the example. Based on this intuition, we formally define different why not yet problems. Let me first give a quick introduction of the symbols used here in the upper right corner. Capital R for the input relation, lowercase r for a tuple in the relation, F for the scoring function used to rank tuples, W for its weight vector, and rho for the rank of a tuple of interest, which is also called the expected tuple in the following. The first problem is the satisfiability problem. Does there exist a ranking function that places Curry in the top 5? On the second line, we present the definition more formally. The next problem, point, asks to return one point, which can be any point, in the solution space. Finally, best asks for the best rank tuple R can reach for any function f. Note that best and point also answers that. To motivate another type of why not yet problem, let us look at an example that shows the limitation of a point solution. Consider this small relation of 3 tuples and 2 dimensions. We want our expected tuple, Curry, to be ranked first. Simply using equal weights for points and assists, Curry only ranks second. A point solution puts Curry in the top spot with a higher weight 0.7 for assists, which seems to suggest that increasing the weight for assists favors Curry. Is that true? Actually not. When we keep increasing the weight for assists to 0.9, Curry drops to the second place again. From the small example, we can see that a point solution does not contain enough information and can be misleading. To address this limitation of a single point, we propose to return a range of points to present more information about weight combinations where the ranking constraints are satisfied. Note that here we have the common constant of all weights adding up to 1 in the example. Hence, there is only one single parameter t. The range of t here provides a lot more information. Curry wins when one with assists much higher than points, but not too much. As we see, the weight for assists can be from 2/3 to 5/6. When we generalize the concept of range in one dimension to multiple dimensions, we introduce the new problem of why not yet box that returns the largest hyperrectangle, inside which every point returns the desired ranking outcome. Okay, next I'm going to introduce our solution to the why not yet problems. For all of them, we must first express the notion of a tuple beating another in the ranking. Remember, we use linear scoring functions, hence we can simply plug the 2 tuples into the function and compute the difference. The more challenging question is to express that at most k-1 tuples beat our expected tuple R, which means R is in the top K. And in other words, R needs to beat at least n-k tuples. But which ones are the tuples to beat among all n-1 tuples? The obvious solution is to try each one of the n-1 choose n-k combinations to look for a satisfiable one. Thus, we may need to explore n-1 choose n-k linear programs, which can be very time-consuming. That's why we came up with a smarter solution, which considers each inequality between R and another tuple to be an indicator. The indicator being 1 means R loses to another tuple. We need the sum of the indicators to be less than k, which means R loses to at most k-1 tuples. Our experiments will show that this dramatically reduces running time and makes the solution practical. And along with the set result, the solvers always return a witness found, hence solving the point problem. By performing binary search on different choices of k, we can also use set to solve the best problem. Now let us explore box, which is a more complicated optimization problem compared to the satisfiability problem. The main challenge here is to enforce that R is ranked top k for each point in the box. When directly encoding this property, we need to use for all quantifiers and the negation in the implication. Especially the use of quantifiers makes the problem much more complicated. Even the current state-of-the-art solvers do not support optimization with quantifiers. So the problem now is, how can we get rid of the quantifiers? That is a tricky one. A classic solution is to explore convexity and monotonicity. For instance, for a monotonic function, we can use the corner points to represent everything in the designed range. This actually looks promising. Notice the similar structure in the direct encoding solution. Unfortunately, it is easy to show that the sum of indicators is neither monotonic nor convex. So what can we do now? Although the sum of indicators is not monotonic, an interesting observation is that each indicator is monotonic. Based on this, we propose what we call a monotonic core solution. In each indicator, we can find a corner point to represent every point in the box. If the indicator is true for this corner point, it must be true for every point in the box. Notice that for different indicators, the corner points can be different. In this way, the quantifiers have been replaced by the simple use of the corner points C here. It makes the solution feasible and efficient, but may result in smaller boxes. For solution 1 with the use of for all, for different points in the box, R can win against the different combinations of n-k tuples. In solution 2, R always wins against the same n-k tuples, which we call the monotonic core. We prove in our paper that any box returned by the monotonic core solution satisfies the direct encoding constraints, but the reverse is not true. For the implementation, we generally rely on Groovy, a state-of-the-art commercial solver. Z3 SMT solver is used only for the direct encoding with quantifiers for the box problem. As we mentioned before, neither Groovy nor Z3 supports optimization problems with quantifiers, but Z3 can handle satisfiability problems with quantifiers. Hence, we transform the box optimization problem to a sequence of set problems to implement the direct encoding solution. We can use the same idea of implementing the optimization problem as binary search on the box size, more generally for improved scalability, allowing us to control the trade-off between running time and box size. Our paper discusses more techniques for improving scalability, including removing dominators and dominatees, which cannot influence the ranking of the expected tuple, and clustering similar tuples and using a representative for the cluster to reduce the number of constraints and variables. Our experiment on the best problem compared against the state-of-the-art approaches. Here we call them sampling and tree. Both approaches rely on sampling. The figure shows the best rank found for using different approaches for each tuple, originally at an odd rank between 20 to 50. The axes show the original rank and the output best rank respectively. On the right, we use a box to show what techniques are on for this experiment. Our proposed approach always returns the correct result, while the competitors often cannot find the correct best rank, even when they are given 10 times more time. For example, see what I'm circling here. For the tuple originally ranked 29, our approach found its best rank to be 18, while the competitors all failed to find the correct best rank. Using about 10 times longer time, the tree approach returned 19, and the sampling approach returned 20. We also verify our point made earlier, showing that indicators is much better than the brute force approach. The x-axis shows the number of tuples and the y-axis shows the execution time. From the figure we see, using indicators is much faster. Here I need to point out that the number of tuples is just at most 50 here, but our techniques can handle 10 to the power of 5 tuples. Here we show the power of our proposed monotonic core approximation compared to the exact solution with quantifiers and named the direct encoding before. The x-axis shows the execution time ratio of the monotonic core solution to the direct encoding solution. The y-axis shows the perimeter ratio, which represents the approximation quality. From the figure, we see the points gathering towards the upper left corner, which means faster execution and high quality. To conclude, we propose various why not yet problems as well as efficient solutions. We list them again in the box on the right. We define 4 why not yet problems: set, point, best, and box. We propose the indicator solution and the monotonic core solution to solve the problems. For improved scalability, we come up with 3 techniques: binary search, clustering, and removing dominators and dominatees. In the future, there is a lot we can explore following this work. For example, for this paper, we consider fairness to be subjective, decided by users. But we can also apply it to group fairness. For example, in our story, we asked, why has Curry not shown up yet? We can ask another question, why has no small forward shown up yet? Then we can think about whether this formula is biased against small forwards, which becomes a group fairness problem. Also, now we have solved the point problem, so we can also look for the nearest point in case we want to apply minimal changes to the original function. And since we have made a step from point to box, we can think about the entire space. That's actually a more challenging problem. Okay, that's all my presentation. Thanks for listening.